But let us consider our shortcut that is generally taken. And the shortcut is, for hardware, that make the problem into a combinational circuit testing problem. And now there can be two kinds of sequential circuits. You can have sequential circuits without feedback. So they often look like this, that here you have some resistor, and here you have some combinational logic. Here you have some resistor. So here you have the lines. So this is an example where you have so these are resistors. So this is a sequential circuit, but it does not involve a feedback. The other possibility is that you can have a sequential circuit with feedback. Now that is where things become kind of interesting. And basically, the thing is that you have some combinational circuit here, and you have some storage elements here. So these are some flip-flops, some registers. There's the clock there. So in this case, now there's an approach here which is referred to as a BIST, and I'm going to talk about this. Now in this case, there is an approach that we can call, general term, designed for testability, and I will mention about that. Oh, let me mention about BIST. Oh, incidentally, yesterday I was attending there's an international board test workshop, and I was in that workshop yesterday, and that is hosted by Intel people here. And basically I'm collaborating with Yashwant here in electrical engineering, and we are doing some work which is trying to statistically analyze data to identify devices that could be bad. But anyway, so I was, and most of the attendees, so two of us, me and Yashwant in electrical engineering, so two of us were the only academics in that group. Everyone else was from industry, and I think most of them are managers. So there was a lot of discussion about BIST. So that, it turns out, for hardware, that is a really popular technique. So we are going to talk about BIST briefly, and so we are going to consider both circuits. So we are going to take a look at BIST, and we are going to look at other issues, other approaches. Now there is an approach which is the extended D algorithm. The D algorithm that we have seen, it will work here also, but it would take more work. So we are going to talk about these two situations, and we are also going to talk about incremental testing for complex systems. So if you have a really complex system that you want to test, so sometimes you want to test a little part of it, and then test a slightly bigger part of it, and then test slightly bigger until you have tested the whole thing, and which is sometimes called the start small approach for testing, which actually works for both hardware and software. I will mention about that. Now in general, since some of us here are from ECE, I should mention that there are a few issues involved. One of them is functionality. You want to make sure that you have correct functionality, and that is what we are going to look at. Other issue is timing. So remember, you have this loop and propagation delay from source to destination, and if your delays are too long, then it will work incorrectly. So there are some issues that have to do with timing. Actually, even signals traveling too fast can be a problem. And so if you have a if you are using latches here, then you will have a problem with that which is called race around. But the typical double clocking scheme would actually make sure that that problem doesn't arise. And now we are going to assume that the faults, this is a combinational circuit, we are going to assume that the faults are only in the combinational circuit. Now, do you think that is a good assumption? So, in other words, we are going to assume that in storage elements there are no faults. We actually did a study. So, a few years ago, we had a PhD student, and he looked at these different flip-flops, different storage elements of different designs, and we got all different designs, and we injected faults in those designs, opens and shorts, and we analyzed the behavior, and it turns out that in many cases, if you have a storage element, let's say this is a D flip-flop, and here is output, let's call it Q, and here is the clock. A lot of times, a fault could be would appear as if this or this is stuck at 0. And if that is true, then you could assume that if let's say you have a fault here, then instead of assuming that the fault is here, you could assume that the fault is here in this line. So, so even though you are considering only faults in the combinational logic, you will implicitly consider faults in the storage elements. So, faults at the inputs of these elements can be considered as faults in the output of this combinational block. Faults at the output of this can be considered to be faults in the inputs of this combinational block. However, there are some failure mechanisms that cannot be modeled as this or this stuck at 0. And if you want the details, you should find our paper, which if you will look at the slides, so we have given references to a couple of our papers on related issues. So we are going to assume that the faults are in the combinational circuit, and so let us consider the case of sequential circuits without feedback. Now, how can we convert the problem into the problem of testing a combinational circuit. So here is basically the approach. Here's the thing. Here we have register A. Remember, a register is a row of flip-flops. And here we have some combinational circuit. And notice that this means that I'm considering all possible lines there. So this is the set of lines. Here is register B. I've sometimes wondered which is a better option, chalk or that those whiteboard with markers. Actually, I always get chalk on your hand. I used to have a professor when I was a student. He actually had a silver thing, so he would put his chalk stick in this silver thing, and then he would write, so that he would avoid getting chalk on his hand. And the chalk is probably less toxic than those colored things. Because if you smell those colored markers, they smell funny. Whereas, I think our bodies need calcium, right? So chalk is probably mostly calcium carbonate.
Well.
So it may be good for us to inhale some chalk dust.
Chalk is bad for your throat.
Allergies.
Yeah, I think, yeah, so if you're allergic, yeah, it could be bad for your throat. And also, I think there are I think chalk also has some silica, which is basically fine sand, and the sand is supposed to be bad for you or something. But anyway, so so this is the problem we want to consider. That is the case, sequential circuit without feedback. So this is a without feedback case. Now it turns out that, so here's the problem. You want to test this combinational circuit. All the faults are in the combinational circuit. That's our assumption. So, let us assume that we have generated a bunch of tests for testing the combinational circuit. Then, our challenge then is, how do we apply the tests here? This is one challenge. And secondly, how do we look at the response and so that we can ensure that the response is correct? And we can do it in this way. Let me write down the steps here. So first you generate test vectors. And then place a vector in A. Now if it is a register, putting a vector in A is probably not hard. You just put it in there, somehow bring it in, and then examine response in B. Now here, these things, so we have steps 2 and 3. Now how can we how can you do those? Now notice that this could be maybe a testing This could be a block within a processor.